Hello. So I'm Lionel Zoubritzky. It's very nice to see you all. I've been a Julia user for more than 8 years now, and I also teach Julia actually at École des Mines. And today I'm going to talk to you about material science, but don't worry, there will also be some computer science as well. And specifically, I'm going to talk to you about crystals. A crystal is a state of matter in which the atoms are organized according to a pattern. And this pattern is repeated periodically across space. So if you zoom in on a crystal, and crystals are absolutely everywhere, like a grain of salt, for instance, you're going to see something like what's on the right, okay, with this organization. Now, crystals are extremely useful for material science, so they are very much studied. And there is a class of properties which are called the topological properties, which are everything that can be derived from the network of chemical bonds, okay? And so if you look at the crystal, and if you take every atom as a vertex and every chemical bond as an edge, what you're going to get is a graph. And it's going to be a periodic graph because the crystal is periodic. Okay? We're going to call this periodic graph a net. And the question which I am interested in is trying to identify nets, which is to find the name of the net. So that we can say, for instance, well, this net is QTZ. And the only QTZ material with composition of silicon and oxygen is quartz. So this helps identifying crystals. Now, how can you find the name of a net, or more generally of a graph? This is actually a quite difficult question, and it's called graph canonization. And it's a superset, it's a super problem harder than graph isomorphism, for which we don't know currently whether it's NP or not. So, in practice, if we have a net, so imagine that this graph here is actually infinite periodic. The first thing which we need in order to have a computational representation of this graph is to choose a unit cell, which is a box that will get repeated across space to make the graph. So we choose the unit cell, which is the blue box here, and we also choose a numbering of the vertices. So let's say that vertex in black is number 1, vertex in white is number 2. Once we have this, we can attribute to each edge a sequence of numbers. So the red edge here is going to be called 1, 2, because it goes from node number 1 to node number 2. 0, -1, because it goes into the unit cell with an offset of 0, -1 compared to the reference unit cell. We can do this for all the edges of the graph, all the unique edges that will get repeated, and we obtain a key. And the key is just a sequence of numbers. So, are we done? Can we say, well, the key is the name of the net? Not really, because this key is not actually unique. Even though the key identifies the net is not identified by the key, which means that in practice, if you change, for instance, the order of the axes, you will get a different key. If you renumber the different vertices, you will get a different key. Even worse, if you move the unit cell, you will get a different key. And even worse, there is actually an infinite number of unit cells for the same graph. So the question of finding a unique sequence of numbers that identify the graph is difficult. In practice, it's solved by the so-called sister algorithm, which was developed by Olaf Delgado Friedrich. And the idea is that we're going to find a topological genome, so actually a key, and we're going to take it as the lexicographically smallest among a finite set. Unfortunately, I don't have the time in 10 minutes to explain you the details of the sister algorithm, so I'm going to only give you a hint of how it works. The idea, the crucial idea, is that we're going to embed the vertices of the graph into a space in a unique fashion, unique up to translation and rotation. And once we have this unique embedding, then we can extract a finite set of representations from which we can extract a finite set of keys, and we can take the smallest. And if we want to have the name of the net, we can just look up topological databases with this topological genome to get the name. Now, how do we position vertices in such a unique way? Well, it's actually quite simple. We only have to solve a linear problem. Ax equals b. X will be the coordinates. A will be a matrix that makes it so that each vertex is going to be at the barycenter of all of its neighbors. And this barycentric placement is unique up to translation and rotation. So we just have to solve this, and it's actually a quite easy problem to solve in Julia. But the difficulty is that I need to have an exact answer. And by exact, I mean that I cannot afford to have any floating point approximation. So luckily for me, A and B are integer matrices. A is actually a sparse matrix. So X will be a matrix of rational numbers. That's the answer which I am looking for. And so I implemented this sparse integer exact rational solver in a separate package, which is available here if you're interested. So let's talk about performance. CrystalNets, which is the package which I implemented for doing all this topological analysis, is the green cloud here. And as you can see, it's about 100 times faster than the reference implementation of sister algorithm in both Java and JavaScript. This speedup is quite significant since I am using my software for analyzing databases of millions of structures. So I need to have something which is quite fast. An additional perk is that CrystalNets, the software, can take as an input not only the graph itself, the periodic graph, but directly the crystallographic file which the chemists, experimentalists obtain from their measurements. So what is actually given to CrystalNets is something like that, where you have only the nature of the atoms and their positions. And what CrystalNet is going to do is first to identify the bonds, and this is a still active research topic, to find chemical bonds in a structure. So I'm using a rather simple algorithm which is completed by a ton of heuristics, basically. And then the second thing it's going to do is to cluster together the relevant atoms into, for instance, the blue clusters which will be the organic atoms and the ochre clusters which will be the inorganic atoms. And from this clustering, we can extract the net, which has a topological information. And finally, we can run this modified sister algorithm to get the name in the end. So why Julia for this particular application? Well, to make it very quick, Julia is easy to program and it's very fast at execution. That's the main thing for almost everything. I need something quick because the algorithm is actually quite complex. I need something fast because I need to run this algorithm on many, many different structures. So in particular for CrystalNets, there are many more specific reasons. I think the main one is the first, which is that I'm doing many, many custom graph operations, and those cannot be vectorized. So basically, I can't use Python if I want to have any kind of performance for this kind of application. And also, programming in Julia is fun. So, it's always something nice. Another thing which I'd like to mention is that the public for my software are the experimental chemists, experimental material scientists. And those people usually do not know how to program at all, much less in Julia in particular, but no programming at all. So I need to have something which can be easily used by people who do not have any programming background. And to do so, what I made is simply a web interface. And the idea behind that web interface is simply that the user will input the file here. They will choose all kinds of options. All kinds of options if they need to, and their request will be sent to the server. So the server is written in Python because it's the lab website. I didn't choose this, and this Python server will call Julia. And the trick is that if you want to have a reactive server, you can't afford to pay the latency of Julia compilation each time. So to avoid this, Julia is running in a separate process, which is daemon mode. If you don't know about daemon mode, I highly encourage you to look it up because it's very efficient for avoiding this latency issue. So Julia is basically running in a separate process, and whenever a request arrives in the Python server, it will forward it to Julia, which will immediately answer because it has been warmed up before. And then we can send back the answer. That's about it. Thank you for your attention. I will be glad to take any question.
Can you maybe give us a flavor of what the algorithm for computing the bonds is?
Sorry?
For computing the bonds
Sure.
from the atoms, what type of algorithm is this? Okay.
So the idea is that first I'm going to take the repeated periodic bond around the atom which I am interested in. I'm looking at the different distances. I will take the shortest distance because that's usually what matters. And then if I will have a criterion on the distance, depending on the van der Waals radius of the different atoms. That's a simplistic option. And then I'm using heuristics to remove bonds which are extraneous. So if I have triangular bonds, for instance, usually the longest one must be removed and stuff like this.